Did NASA's James Webb Space Telescope notice a planet in a far-off, nearby planet group that could uphold life? In a pivotal moment for cosmology, the James Webb Space Telescope has pierced the vastness of space to capture an image beyond our solar system. This isn't just any image. It's a discovery that could reshape our understanding of the universe. Today, in this discussion, we will examine the new image captured by the James Webb Telescope that could reveal mysteries about habitable planets. In 1963, Russian astrophysicist Nikolai Kardashev introduced a groundbreaking concept to measure the developmental progress of civilizations based on their energy consumption. Known as the Kardashev scale, it was developed while studying the quasar CT-102 and pondering the existence of extraterrestrial civilizations far more advanced than humanity. The scale classifies civilizations into three types. Type 1 harnesses the entire energy of their planet. Type 2 utilizes the full power of their host star. Type 3 exploits the energy of an entire galaxy. Do you know where Earth stands on this scale? Let us know your thoughts in the comments section below. The Dyson sphere, proposed by physicist Freeman Dyson, is a theoretical structure for capturing a star's total energy. Variations include the Dyson swarm, a collection of orbiting solar collectors, and the Dyson shell, a massive star-enclosing structure often featured in science fiction. These constructs would shift a star's radiation toward infrared frequencies, aligning with energy conservation laws. In 2016, NASA's Curiosity rover made an unexpected discovery when it found tridymite in a rock sample from Mars' Gale crater. This challenged previous beliefs about Martian volcanism. Experts later explained that the mineral likely formed in an underground magma chamber before being ejected during an eruption. This discovery has significant implications for understanding Mars' geological history. The 2018 discovery of organic molecules on Mars by the Curiosity rover sparked great interest in the search for Martian life. Fluctuating methane levels on the planet have led to theories ranging from comet impacts to possible microbial activity. While meteorites like the Nakhla meteorite offer intriguing clues with their complex carbonaceous materials, the question of life on Mars remains unsettled. The InSight mission, which landed on Mars in November 2018, has been studying the planet's geological structure with a heat probe and seismometer. It recently recorded its strongest quake yet, with a magnitude of 5, puzzling experts about its origins. On February 18, 2021, NASA's Mars 2020 mission landed the Perseverance rover and Ingenuity helicopter on Mars to explore the possibility of past microbial life and prepare for future human missions. Perseverance will analyze rocks for biosignatures, study the planet's atmosphere and geology, and convert CO2 into oxygen. NASA's James Webb Space Telescope recently identified an exoplanet, K2-18b, located beyond our solar system, which shows potential to support life. The telescope detected methane and carbon dioxide on this planet, which is around 8.6 times larger than Earth. These findings suggest that K2-18b may be classified as a Hycean exoplanet. Exoplanets refer to planets located outside our solar system, and the term Hycean is derived from merging hydrogen and ocean. It describes planets believed to have hydrogen-dominated atmospheres combined with oceans of liquid water, as explained by Space.com. Moreover, dimethyl sulfide, DMS, is potentially present on K2-18b. On Earth, DMS is a compound naturally associated with living organisms. According to NASA, K2-18b is located within the habitable zone, suggesting its proximity to its star could allow the presence of water on its surface. Such regions are often called Goldilocks zones, inspired by the classic children's story, implying conditions that are just right for life. The planet exhibited high levels of methane and carbon dioxide with an apparent absence of ammonia. This hints at the possibility of an ocean beneath K2-18b's hydrogen-rich atmosphere. NASA's observations suggest that the presence of DMS on the planet has led scientists to hypothesize about the potential for life there. This is because, on Earth, DMS is produced by phytoplankton, a type of marine algae that serves as a food source for marine life, and is synthesized through sunlight. Nika Madhusudhan, a respected astronomer from the University of Cambridge and the primary author of the study, stated that future observations from Webb should determine whether significant amounts of DMS actually exist in K2-18b's atmosphere. K2-18b, situated within the habitable zone, is known to contain carbon-based molecules. However, this doesn't automatically imply it can support life. Given its considerable size, about 2.6 times Earth's radius, the planet is believed to have a vast mantle of high-pressure ice, similar to Neptune. Yet, it could also have a thinner hydrogen-rich atmosphere and a surface ocean. While high-pressure worlds are theorized to contain immense water oceans, there's also a possibility that K2-18b's ocean might be too hot to sustain life or remain in a liquid state. Subhajit Sarkar from Cardiff University clarified that while our solar system doesn't have a planet of this kind, subneptunes are the galaxy's most common planet type. Their precise location within a habitable zone has allowed us to identify atmospheric particles. Characterizing exoplanet atmospheres, which involves determining their gases and conditions, is an emerging field in astronomy. However, the brightness of their much larger host stars often overshadows these planets, making their atmosphere challenging to study. To overcome this, the team analyzed light from the K2-18 star as it passed through the planet's atmosphere. Being a transiting exoplanet, K2-18b causes a dip in brightness as it moves across its star's face. This method led to its initial discovery in 2015 through NASA's K2 mission. During such transits, a tiny fraction of the starlight passes through the exoplanet's atmosphere before reaching instruments like the James Webb Space Telescope. This journey of starlight through the atmosphere creates identifiable imprints, enabling astronomers to infer the atmospheric gases of the exoplanet. The exceptional sensitivity and extended wavelength range of the Webb telescope made it possible to detect spectral features with just a few transits, as highlighted by Madhusudhan. To put this in perspective, a single transit observation with Webb offers precision comparable to 8 Hubble observations conducted over several years within a narrower wavelength range. Savas Constantinou from the University of Cambridge added that the current results, based on just 2 observations of K2-18b, are only the beginning. They demonstrate Webb's potential to study exoplanets within the habitable zone. Their findings have been approved for publication in the Astrophysical Journal Letters. The research team is preparing for further studies using Webb's MIRI mid-infrared instrument spectrograph. They anticipate this will validate their current results and shed light on the conditions surrounding K2-18b. Madhusudhan concluded with a broader vision. Our ultimate goal is to identify life on a habitable exoplanet, reshaping our understanding of our place in the universe. Current insights mark a significant step toward understanding Hycean planets in this grand journey. The research into exoplanets like K2-18b signifies a transformative phase in astronomy. It opens up opportunities to explore worlds vastly different from our own, with environments that may still support life. By using cutting-edge technologies such as the James Webb Space Telescope, scientists are unraveling the mysteries of distant planetary systems, one discovery at a time. What's next in the search for life? The findings on K2-18b are just the tip of the iceberg. Future observations with Webb will focus on refining our understanding of its atmosphere, confirming the presence of key biosignatures, and assessing its habitability potential. Researchers are particularly excited about Webb's ability to explore other similar Hycean exoplanets, given their prevalence in the galaxy. To complement these efforts, other missions like the European Space Agency's Aerial Telescope, slated for launch in the early 2030s, will conduct detailed studies of exoplanet atmospheres. The goal is to build a comprehensive catalog of potential biosignatures across a wide range of planets. NASA is also developing advanced space telescopes, such as the proposed Habitable Worlds Observatory, which could provide even more precise data on Earth-like planets in habitable zones. Combined with ongoing ground-based observations, these missions will strengthen the search for extraterrestrial life. Broader implications of exoplanet research. The study of exoplanets isn't just about finding life. It also helps scientists understand the formation and evolution of planetary systems, including our own. By studying planets like K2-18b, researchers can piece together clues about how planets form, the role of their host stars, and the conditions necessary for life to emerge. Moreover, exploring diverse planetary environments challenges long-held assumptions about what makes a planet habitable. For example, the discovery of Hycean planets expands the criteria for potential life-supporting worlds beyond Earth-like conditions, showing that life might thrive under completely different circumstances. Challenges ahead. Despite the exciting progress, significant challenges remain. Observing distant exoplanets with precision is technically demanding. Instruments must detect faint signals amidst overwhelming noise from their host stars. Additionally, interpreting data about atmospheric composition requires careful calibration and validation to rule out non-biological sources of observed gases. Another challenge lies in distinguishing between potential biosignatures and false positives. For instance, gases like methane can be produced by both biological and non-biological processes, making it essential to consider the planet's overall context when assessing habitability. The philosophical impact of finding life. If scientists eventually confirm life on K2-18b or any other exoplanet, the implications would be profound. It would not only reshape our understanding of biology, but also challenge humanity's perception of its place in the cosmos. The discovery of extraterrestrial life could spur philosophical, cultural, and even theological debates about our role in the universe and the uniqueness of Earth. Madhusudhan and his team remain cautiously optimistic as they continue their investigation of K2-18b. As he stated, while the search for life is a daunting task, every discovery brings us closer to answering one of humanity's oldest questions. Are we alone in the universe? A global collaboration. The journey to uncover life beyond Earth is a collective endeavor involving scientists, engineers, and institutions from across the globe. From NASA's pioneering missions to contributions by international space agencies and universities, the study of exoplanets exemplifies the power of collaboration in pushing the boundaries of knowledge. As the James Webb Space Telescope continues to deliver groundbreaking results, humanity stands on the brink of a new era in astronomy. Each observation brings us closer to unlocking the secrets of the cosmos and perhaps, one day, finding a distant world teeming with life. While the journey for extraterrestrial life has generally focused on modest, Earth-like planets, extensive Hycean planets present a better climate for atmospheric studies. As our continuous journey through the universe proceeds, the James Webb Space Telescope emerges as a symbol of mankind's creativity, uncovering the universe's hidden mysteries. Can the James Webb Space Telescope find evidence of life beyond our planetary system? As our understanding of the universe expands, the discovery of potentially habitable exoplanets becomes increasingly critical. The James Webb Space Telescope, JWST, is at the forefront of this investigation, offering extraordinary capabilities to study distant planets. The telescope's ability to analyze exoplanet atmospheres and detect specific gases is revolutionizing the way scientists approach the search for life beyond Earth. By studying the chemical composition of these atmospheres, experts can infer conditions that may be suitable for life and refine the criteria for habitable planets. One of the most remarkable aspects of the James Webb Space Telescope is its ability to observe exoplanets in the infrared spectrum. Infrared light allows astronomers to peer through thick clouds of gas and dust that often obscure visible light observations. This capability has proven essential in studying distant worlds like K2-18b, where the telescope has already provided critical data. Webb's sensitivity to infrared radiation enables the detection of spectral features that indicate the presence of molecules such as methane, carbon dioxide, and dimethyl sulfide, DMS, all of which could signal biological processes. These molecules are considered potential biosignatures, compounds that may be produced by living organisms. The discovery of DMS on K2-18b is particularly intriguing. On Earth, DMS is primarily produced by marine phytoplankton, which play a key role in Earth's ecosystems. The presence of such a compound on K2-18b raises the possibility that life could exist there, or at the very least, that the planet has conditions capable of supporting life. While the detection of DMS is not definitive proof of life, it suggests that K2-18b might have an environment conducive to biological activity. Scientists are hopeful that future observations will help clarify whether the presence of DMS on K2-18b is evidence of life or merely the result of other processes. Beyond atmospheric analysis, JWST's ability to study the physical characteristics of exoplanets is also enhancing our understanding of these distant worlds. For instance, the telescope can measure the size, temperature, and surface conditions of exoplanets. By studying the size and mass of a planet, astronomers can estimate its density and composition. This is crucial because the presence of liquid water, a key ingredient for life as we know it, depends on a planet's temperature and atmospheric pressure. Planets like K2-18b, located in the habitable zone of their star, might have the right conditions for liquid water to exist on their surface. However, not all planets in the habitable zone are suitable for life. The size of a planet plays a pivotal role in determining its habitability. For example, K2-18b is much larger than Earth, and its size suggests that it may have a thick atmosphere and high pressure, which could make it hostile to life. It is also possible that K2-18b has an ocean beneath its atmosphere, but this ocean might be too warm to support life or could exist in a gaseous state due to high temperatures. Despite these uncertainties, the fact that the planet exists in the habitable zone of its star and shows signs of having an atmosphere rich in key molecules makes it a promising candidate for further study. The discovery of planets like K2-18b is part of a broader effort to identify potentially habitable exoplanets. Astronomers use various methods to detect and analyze exoplanets. The most common technique is the transit method, which involves observing the dimming of a star's light as a planet passes in front of it. This method allows scientists to determine the size and orbital characteristics of the planet. Other techniques, such as radial velocity and direct imaging, are also used to study exoplanets, but the transit method has proven to be the most effective for identifying planets in the habitable zone. While the search for habitable exoplanets is still in its early stages, the potential for discovering life beyond Earth is becoming increasingly realistic. The identification of exoplanets with Earth-like conditions could provide valuable insights into the origins of life in the universe. For instance, studying the atmospheres of these planets could help scientists understand how life might arise on other worlds. By identifying planets with similar atmospheric compositions and environmental conditions to Earth, astronomers could gain a better understanding of the factors that make a planet suitable for life. The James Webb Space Telescope's contributions to this field are just beginning, and future missions are likely to build on its findings. As the telescope continues to observe distant exoplanets, scientists hope to uncover even more evidence of habitable worlds. The ability to detect and study exoplanet atmospheres in such detail is a game-changer for the field of astrobiology. With each new discovery, the possibility of finding life beyond Earth becomes more tangible. Beyond its scientific implications, the discovery of potentially habitable exoplanets raises profound philosophical questions. If life is found on another planet, it would challenge our understanding of our place in the universe. The existence of life elsewhere could suggest that life is common in the universe and that Earth is just one of many planets where life has emerged. Conversely, the absence of life on other planets could imply that life is a rare and precious phenomenon, making our planet even more unique. These questions are not merely academic. They have the potential to transform how we view ourselves and our future. As we continue to explore the universe, the search for extraterrestrial life will likely become a central focus of human exploration and scientific inquiry. The James Webb Space Telescope, with its groundbreaking capabilities, is playing a pivotal role in this endeavor. As we learn more about exoplanets like K2-18b, we may be one step closer to answering one of humanity's most enduring questions. Are we alone in the universe? The discovery of potentially habitable exoplanets, such as K2-18b, also underscores the importance of space exploration in the broader context of human survival. While colonizing other planets is still far from reality, the study of exoplanets and the search for life beyond Earth could inform future efforts to preserve and sustain life on our own planet. Understanding the conditions that support life on other worlds may offer insights into how we can address challenges such as climate change, resource depletion, and the sustainability of human civilization. The James Webb Space Telescope is not only advancing our understanding of distant worlds, but also serving as a testament to human ingenuity and collaboration. The telescope is the result of decades of scientific effort, technological innovation, and international cooperation. Its groundbreaking capabilities provide a glimpse into what humanity can achieve when nations and institutions come together with a shared vision. As more exoplanets are discovered, scientists are developing new frameworks to categorize their potential for habitability. Beyond the habitable zone concept, researchers are exploring other factors that could influence a planet's ability to support life, such as the presence of magnetic fields, geological activity, and the stability of its star. These additional criteria are helping refine the search for worlds that might harbor life and provide a more nuanced understanding of planetary systems. The role of artificial intelligence and machine learning in this research is also becoming increasingly significant. Advanced algorithms are being used to analyze vast amounts of data from telescopes like JWST, helping scientists identify subtle patterns and anomalies that might indicate the presence of exoplanets or biosignatures. AI-driven models are also being used to simulate planetary atmospheres and predict how they might evolve over time, offering valuable insights into the dynamics of distant worlds. Future missions are expected to complement JWST's capabilities, further enhancing our ability to study exoplanets. Projects like the European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, and NASA's upcoming Habitable Worlds Observatory aim to build on Webb's findings by conducting more detailed surveys of exoplanetary atmospheres. These missions will help answer critical questions about the diversity of planetary systems and the prevalence of conditions suitable for life. The quest for extraterrestrial life is not just about finding other living organisms. It is also about understanding our own existence. Discovering even the simplest forms of life on another planet would have profound implications for biology, philosophy, and our sense of identity as a species. It would demonstrate that life can emerge independently under the right conditions, expanding our understanding of the universe's potential for diversity and complexity. Conversely, if we find no evidence of life after decades of exploration, this too would be an important revelation. It would suggest that life, as we know it, might be an incredibly rare occurrence, emphasizing the need to cherish and protect our own planet. This perspective could inspire greater efforts to address global challenges and foster a sense of unity among humanity as we face a shared future on Earth. The James Webb Space Telescope has already transformed our understanding of the cosmos, but its full legacy has yet to unfold. As it continues to explore the far reaches of space, it will not only enhance our scientific knowledge, but also inspire new generations to dream, innovate, and seek answers to the universe's most profound mysteries. Whether it ultimately reveals the presence of life beyond Earth or underscores the uniqueness of our planet, the telescope's contributions will shape the trajectory of human exploration and understanding for decades to come. In the end, the search for life beyond our solar system is as much about discovering the universe as it is about discovering ourselves. The more we learn about distant worlds, the more we reflect on our place within this vast cosmic expanse. The James Webb Space Telescope, with its unprecedented capabilities, serves as both a scientific tool and a philosophical beacon, guiding humanity toward a deeper connection with the universe and our shared existence within it.